Let's get started. Welcome to part 2 of the course. I can't believe it's been almost 7 weeks since I first came up here, welcomed you to the program, welcomed you to the course, and you've done your first midterm, so you're halfway through. The midterm, hope you don't feel too traumatized by it. It's supposed to be a checkpoint, right? The first midterm especially, it's open book. It's really testing the absolute fundamentals. If you really struggled with it, it should set off alarm bells. If you cruise through it, that's good, but it doesn't mean you're home and dry. Second midterm will be a bit more challenging, and the exam certainly even more challenging. But it's a process. So if you keep up with the material, if you do the exercises, you'll be fine. So this poster, I normally put this up in previous years when I've taught the entire course. I put it up in week 2, and the students look at it and they think, it looks very fancy. Some of them freak out when I tell them that this is not just an arbitrary poster, because every single equation on this poster you're going to see, and I guarantee you, by the end of the program, you will understand every single one of them. Okay, you're halfway, so I'm guessing that you recognize most of them. Today, we're going to focus on this part here. Okay, sort of middle left. Actually, today's a big session. So today, you're going to derive the Black-Scholes pricing formula. Okay, so it's a big session. You've looked at deriving the partial differential equation, which is, it's one of the most important equations in science, right? Certainly in finance, it's the most important equation, but even broadly speaking in science, the Black-Scholes partial differential equation is up there. I've attended lectures in engineering and physics where they talk about the heat equation, the Navier-Stokes equation, for those of you who are from a fluid mechanics background, and Black-Scholes comes up as well. Okay, so it's up there. It's one of the most important equations in science. Today you're going to learn how to solve it. Okay, so it's a big session. I'm going to try to keep today's session a little bit short. I understand you've all had a midterm, you've all had to rush back, so we'll try to keep today's session a little bit short, but it is a very important session. Now before we get started, just a couple of admin points. A couple of notes. So the second midterm will be on Thursday, the 6th of November, okay, at 7 p.m. It'll be a very similar format to the one you did today. Open book, but no electronic devices, individual test. The venue will be decided shortly, and I will circulate that once it's confirmed, okay? The second note, something I mentioned right at the beginning, but just to remind you, there will be no lecture on Thursday, the 23rd of November. Okay? That will be replaced, and I'm sorry to be the bearer of bad news, but it's been replaced with a Saturday lecture from 2 to 5 p.m. in this lecture theater. Okay? So a couple of points just to bear in mind. And I think I've made an announcement on Canvas already, so please bear that in mind. Okay, before we start off on week 8, I just want to go back to week 7. I just want to refresh a few things, okay? Things that we're going to need for today. But things that are important, nevertheless, for the program. You've looked at that equation. You've seen that equation. You know where it comes from. Okay, it comes from economics. You should understand all the economic reasoning behind how this equation is derived. Okay? Certainly for the exam, okay, you should be able to derive this from first principles. Okay, the maths is not difficult, it's all economics. So you need to be comfortable with things like self-financing strategy, the idea of replication, a hedging portfolio. Okay? The underlying modeling assumptions, which is the log-normal stochastic differential equation. What is that? You need to know what it is, how you solve it, how you arrive at this partial derivative. How it changes if you've got a dividend paying stock, continuous dividend yield. And then you did a bit of maths. I think last week, or was it the week before, we introduced Monte Carlo. Okay, so that was kind of like a detour. You probably had a session where you didn't do any finance. You just talked about Monte Carlo, random numbers, expectations. You spent a bit of time doing that, and today really, or last week at the end, we asked the question, well, what's the connection? Did Monte Carlo, you have this PDE, where do they link? And that's where the idea of conditional expectation comes in, because there are these really nice formulas or theorems, Dinkin's formula, but really the more important one is a slight variation of this, which is the Feynman-Catch formulation. This is an important result. There's not much going on here, okay? You've got a random variable S. You're trying to solve the partial differential equation. What does solving the partial differential equation even mean? Okay. All it means is figuring out a function v, which when you plug it in here, it all works. A function v is a function of time and of s. Okay, those are the variables. And it's important to distinguish between variables and parameters, which we'll talk about today. But essentially, s and t are variables. So you need a function v, which is a function of time and s. You take the first derivative with t, you take the first derivative with s, second derivative, you put it all together, magically it all equals 0. As soon as you identify this function, you have a candidate for the pricing formula of a derivative. Okay? Convince yourself, you've already seen a few derivatives. You've seen the money market account, that's a derivative. Right? Remember way back week 1? It's a derivative which pays $1 at some time in the future. Okay? In this case, the derivatives with respect to s are 0. Take the derivative with respect to t, plug it in, you see it comes up to 0. Okay? Forward price, you've worked out the value of a forward contract, plug it in, it works. Okay, so that's what it means to solve the PDE. Come up with a function. And today we're going to come up with a function using expectations. But to do that, we need to see the connection, right? And the connection comes here. S is a random variable, so any function of S is a random variable, right? More specifically, S at time capital T in the future. Okay? If you take the Taylor expansion of this, you get standard result. First derivatives, second derivatives. You keep the second order in S because of the Ito correction. The integral is just standard Taylor expansion. And then you take expectation. Okay, what I haven't shown here is there's an additional term, which is the Ito term, which disappears because you took the expectation. Right? The expectation of an Ito term, of an Ito integral is 0. Okay, more specifically, you're taking the conditional expectation, conditional on all the information you have today, which is time 0, s 0, and you come up with this result, which is a perfectly general result. But if you apply it to the special formulation of f, which is just written in this way, this is the thing we're after. Okay, that's the pricing formula. That's the function which defines the value of a derivative. Okay, that's what we're trying to find. If we write f in this way, plug everything back in. Okay, and it's just simple calculus. I'm not going to go through it, but you can take the derivative of f with respect to t. There's two terms there because you apply chain rule. Derivative with respect to s twice, etc., etc. You get this result. And this is nice, because what do you know about this guy? Okay, that's 0, because that's what the partial differential equation tells us. So this term completely disappears, and all you're left with is that elegant result. Okay? That is the risk-neutral framework. Okay? The partial differential equation has been translated to an integration. You have a choice. You can now solve the partial differential equation directly if you wanted to, or you could translate it to to this expectation, solve it, you should get the same answer. Okay, two ways of solving the same thing. And this is what we call risk-neutral dynamics, or risk-neutral framework. Okay, so it's perfectly possible for me, or for you to be asked in an exam, to derive some pricing formula, and the exam will state, the question will state, you may use the risk-neutral framework. Okay? If that statement is made, you can start here. Just start from this point. Okay? You need to remember, of course, that this all works only under this special case, where the drift is R. Okay? This is kind of like it's almost a magical result, right? This all worked. You're trying to solve for this equation. You've got a partial differential equation. But if you rewrite the dynamics using R as the drift, somehow magically you can write it as an expectation. Okay? That's part of the deal. So you need to remember that risk-neutral dynamics means replacing the drift with R. Okay? And it's not just any drift, it's the continuously compounded drift. Okay? And that's the price of the derivative. And you'll see it in textbooks written as the expectation under the measure Q. And the measure Q is precisely this statistical distribution for S where it drifts according to R, not according to mu. Okay? The expectation under the measure P is normally, P is usually called the subjective measure, Q is usually called the risk-neutral measure for obvious reasons. But if you take the expectation under the subjective measure, where you inject mu into the drift, you don't get the right answer. Okay? That's not the solution to the partial differential equation. You'll get a number, it'll be the wrong number. Okay? So that's very, very important. Risk-neutral framework. Unless you're explicitly asked, you don't need to prove the risk-neutral pricing formula. Okay? So if the question states, use the risk-neutral framework, start there. Okay? Start with this. Just write it down. If the question requires you to prove why this is the case, it'll make it very clear. Okay? And certainly you should be able to prove it. We've just done it over a couple of slides. But the rest of today is really about solving this expectation. Okay? Sorry, quite a long intro, but any questions on that? Okay. So, for today, as I said, I'll try to keep it short. We'll probably stop around there. Okay? I think it's already a long evening for all of you. But I do want to go through the Black-Scholes pricing formula and maybe start on multidimensional derivatives. Okay, so recap on kind of the first modeling point, which is the assumption that the underlying, usually in equity, okay, stock price evolves according to that stochastic differential equation, which makes sense, right? If you had ds is equal to mu s dt, you all know that's just exponential. Okay, that's a terrible drawing, but you get an idea, right? It's an exponential. What we're saying is that with this randomness, you kind of sometimes go up, sometimes go down, but on average, you kind of do that. Okay? And you've already seen that you can solve that stochastic differential equation to get this as the solution. And again, certainly you should be able to do that from first principles. Okay? Not memorizing. With time, you'll memorize it, but you should remember where it comes from. Okay? You should remember that you need this correction here, this half sigma squared t, because in Ito calculus, you've got to take derivatives twice to preserve the quadratic variation. So you need to keep this term, but you need to be able to derive it. And of course, you need to remember that Brownian motion is just, that's the source of randomness. Okay? And it's the nicest source of randomness. It's the Gaussian, right? It's normally distributed, zero mean, and variance, which is just defined by the time horizon over which the Brownian motion is evolved. Okay? Longer time horizon, more uncertainty. Another point is, what if mu, up here I've characterized it as a constant. Mu and sigma are constants. But what if mu and sigma are functions of time? Just straightforward functions of time. They're not stochastic. They're not functions of S. We'll talk about that in a couple of weeks. But what if they're just functions of time? Smooth, given functions. Okay? That's what you end up with. And that shouldn't trouble us. Okay? It shouldn't trouble us because we can integrate it away. You can work out if mu is now a function of time, which you can also write mu t if you want, you can come up with mu hat. Okay? That's really what you care about, the integral of mu with respect to time. Sorry, you can write that as mu hat times t. Okay? So you can always work out some mu hat, which is the average drift over the time horizon you're interested in. Okay? And you can come up with mu hat is just this integral divided by t. Okay? And then you're back in business. Mu hat's a constant for your problem. What about sigma? If sigma is actually a function of time, what do you have? What do you know about this integral? Ito integral, right? And what do you know about the Ito integral? Well, the mean's 0, but more importantly, what is the variance? Okay, you know that this is some normal variable with 0 mean, and let's call it sigma squared bar. If you want, probably a t in there. But again, you can integrate it away, right? You can write this as some sigma, or some variance times z, where z is normally distributed. Okay? Use the Ito isometry. You know that the variance is the integral squared. Okay, you know that from the Ito isometry. So this is the variance of that guy. So if you wanted to write this as some average variance, that's all you do. Okay? You can extract. My point is that things being functions of time shouldn't worry us. Okay? We can always integrate them away, come up with an average for that time period, and we're back in business. We're back into this world of constant drift and constant volatility. Make sense? Any questions on that? Okay, so we want to understand this a little bit more. We've introduced S, but today we're going to integrate over S. We're going to compute an expectation. So we want to understand a little bit more about what we're trying to do. Okay? We're essentially trying to evaluate some expectation of that form. Okay? ST is a random variable. It's in the future. It's a stock price in the future. You don't know what it is. V is a function of ST. So by association, V is also a random variable. Okay? And now if you want to compute the expectation of V, this is standard definition. Right? It's the expectation of V is the integral V of S times the probability density function of S. Okay, you've seen that before. The point I want to try to make is that you've actually got a choice of which coordinate system you work in. Okay, which variable do you work in? S is a function of Vt. Vt is just z times the square root of time. Z is just a standard 0, 1 Gaussian. Okay? All the randomness comes from z. Okay? So you can either work in space of z or space of S. Okay, it's a choice. Both of these expressions will give you the same number, but they're very different. Okay, you're integrating over different variables. I mean, the domain is different. What's z? Z is a 0, 1 standard Gaussian, right? Let's say the domain is minus 5 to 5. Okay, it's minus infinity to infinity. S is a stock price. The domain is 0 to infinity. Okay, stock price can't be negative. So the sample space is different. The probability density function is different. It's just a change of coordinates. Okay, and you need to be very clear which one you're working with. I will work more often than not with z. Okay, the Gaussian distribution is well understood, easy to solve analytically. That's the one we're going to use. Okay, and for most of this course, that's the one you will want to use. But it doesn't preclude you from using this if you ever wanted to. Okay, you've actually seen, you all know what this is. Right? You've seen that. I think problem set 2, you derived that expression. You wrote some Python code. You plotted it. Okay, so you already know what this one looks like. Okay, so be very conscious. The result's the same, but the distribution's different. The underlying random variable's different. Decide which one you want to stick with. Now, once you have a random variable, statisticians, the first question they ask, well, maybe the first one is the one we've already asked, which is, I have a random variable, what kind of values can it take? Okay. And then second, they usually ask, what's the mean? What's the variance? Right? Where's the distribution centered? How far can it drift from that mean? So in other words, what are the first and second moments of S? Okay. We all know the first and second moments of Z. But what are the first and second moments of S? We know that S is a function of WT. Okay, it's the function we saw a couple of slides back. The first moment is the expectation. All of this comes out. The only randomness comes from W, from Brownian motion. Okay? So you're trying to work out the expectation of this exponential. It turns out it all disappears and you get a really nice result. Okay? And to see that, you can solve it directly. You can write down the integral. Okay? You can always write down sigma WT as sigma root T Z, and then just do the integral. Okay, it's a bit of calculus, it's a bit messy. But an easier way is to use this thing called the moment generating function, okay, which is also introduced to you. But the moment generating function, for the purpose of this course, you don't need to be able to derive this. It's not too complicated to do, but it's not really part of this course. The moment generating function, you can look it up as this, okay? Or more specifically, this is the definition of a moment generating function. For the Gaussian, it's this, okay? And you've already seen that with a moment generating function, you can compute first, second, nth moments very easily, okay? So in general, if x is a normal 0 nu squared Gaussian, then the moment generating function is that guy there. What we actually have is sigma times Brownian motion, right, which I've already showed you is actually sigma squared t invariance. That's okay, just plug it in. And what gives you the result is setting m equals 1, right? M is the variable that the moment generating function introduces. And that's it. You get this e to the half sigma squared t, which is what cancels the Ito correction. Right? So that's what it is. Not too surprising, given that what I said up here right, you have a lot of randomness, but if you take the average value, it actually tracks the drift of mu, okay, on average. Okay, that's the first moment. What's the second moment? It's the variance. The definition of variance is the expectation of s squared minus the square of the expectation. We've already got the expectation, so this second term is easy. Already got that? This is the one we need to figure out. Okay, but it's actually no difficult. No more difficult than what we've just done. Okay, because if you write it out again, you can take out all the constant terms. You've still got something that looks very similar to what you had previously. Again, you just use the moment generating function with m equals 1. Okay? Only difference now is that because you've got the term 2 of 2 sigma wt, okay, just because of this term, you get 4 here, you get an extra 2 there. The same idea, right? You just put it all together and you get this term. So you see the mean looks nice. It's not as nice as 0, right? The mean of z is 0. This one looks horrendous. It's the variance of z of s. Variance of z is 1. I'd rather work with z, right? But that's what it is if you ever need to do it. Okay, you should be able to translate between z and s. It's just change of coordinates from calculus. Okay, this is the important part. This is now building up. We're building up to the Black-Scholes pricing formula. Any questions so far? No? Okay. Have you seen Girsanov's theorem already? Okay, you've seen it in one of the other modules, I guess. It is such an important result, I have no problem going through it again. Okay, and maybe this is a slightly different lens, because I'm not going to go through the mathematical rigor. I'm going to state the result as you would use for an application. Okay, so Z is standard Gaussian, and you know that. Okay, you don't have to memorize this, by the way. You probably will with time, but on an exam, I'll give it to you. Okay, you don't need to memorize any probability density functions. Okay, you need to know what to do with them, but you don't need to memorize them. Okay, so let's consider, how do I want to call it, Z squiggle. Okay, Z squiggle is just a function of Z. Okay, there's a Z there, there's a Z there. So Z squiggle is a random variable, right? It's a function of a random variable. Now, just let's go with this. Maybe it's not obvious why we're doing it, but let's say you wanted to take the expectation of this very complicated looking random variable, Z squiggle. Okay, just wanted to work out the expectation, introduce a new random variable. Now you know from first principles that the expectation will just be well, you could do it this way. Let's call this squiggle. Okay, you could do it that way. But you know, what's the probability density function of Z squiggle? Not so obvious. If you work in units of Z, you can also rewrite this as Z times this thing here. With me so far? Okay, I've just chosen to work in units of Z. And what you'll know, if you plug it in, maybe this is something you should do in your time. If you plug in this here, this there, put it together, factorize it, everything's in the exponential, you get something that looks a little bit better. Okay, that's the expectation you're after. Now, what is this? Who can tell me what this is? That's right. That is just a definition of a Gaussian distribution with mean lambda. Okay? Just the mean's changed. The variance hasn't even changed. All that's happened is that you've translated your normal distribution by some coordinate lambda, right? Which means, what is expectation of z in this case? It's got to be lambda, right? Because z is now, by definition, under this if you write it this way, z is no longer a 0-1 distribution. It now behaves as if it's distributed centered on lambda. Okay? So the exponential multiplier just changes the mean of z. In other words, what are we saying? This is the part where some people get confused and say, hang on, didn't we say z is 0-1? Now it's 0 lambda. Sorry, we said it was 0-1, now it's lambda 1. Okay? Well, kind of. Let's be very careful what we're saying. We started off with a problem where our underlying random variable was a standard normal. And we've translated the problem because we're actually trying to solve something a little bit more complicated. Okay, we're trying to solve something a little bit more complicated. And it looks very complicated, but actually we can rewrite it, and z is just a dummy integration variable. It works out to be an expectation of a random variable, which is still Gaussian, just shifted. Okay, that's the important result. Okay, so let's take it further. What if we have f of z, some function of z, and we're still multiplying it by this special exponential term? You convince yourself, you do the integration again, but nothing changes. All that happens is that your PDF, your effective PDF changes. It's now, once more, this shifted Gaussian. Which means that if you're trying to work out the function, the expectation of f, sorry, you were originally trying to work out the expectation of this complicated guy, which was f times some exponential. You can actually work out just the exponential of f. Just the expectation of f. But y is no longer the original 0-1 variable. It's now lambda 1 variable. Okay? So all that this exponential has done has changed the mean of z. Okay, let's take it a step further. We're always dealing with random Gaussians. Okay? Wt, which is Brownian motion, is also a normal. It's not standard because the variance is t, but the same thing happens again. The form of this exponential, which we'll now call the Radon-Nikodym derivative, okay, it's usually given this fancy notation in textbooks, but the form is very similar. It's an exponential. Okay, it's an exponential of something times t plus something times z, right? Although Wt can be written as root t z. Okay? But we do the same thing again. I don't want to repeat because it's really the same result from the last two slides. Just go through it slowly in your own time. If you wanted to work out the expectation of this function, of any function of Brownian motion, what could a function of Brownian motion be? Stock price is a function of Brownian motion, right? Any derivative is a function of Brownian motion. Okay, so if you're ever working out some function of Brownian motion, and you find that you've got this extra exponential term sitting next to it, all you end up with is a new probability density function with a shifted Brownian motion. Okay? In other words, if you want to take the expectation of this complicated thing, it's just like taking the expectation of f, which is slightly less complicated than having a product, but Wt just gets shifted, okay, by some lambda. Let it sink, okay? The obvious question you're probably asking yourselves is, okay, this looks very fancy, but so what? It only works for this very special case. It only works for this very unique special case. Who cares? Well, it turns out that this exponential comes up all over the place in derivative pricing. Okay? Comes up a lot. We're going to see it when we derive the Black-Scholes pricing formula in a couple of slides. And usually we have lambda equals sigma. Okay? This is the Radon-Nikodym derivative with lambda equals sigma. Should look familiar to you. Okay? It should look familiar because up here okay, the solution to the log normal distribution is essentially a minus a half sigma squared plus sigma WT. So that special exponential comes up everywhere. Right? And that just means that if you have some function of WT, it could be any function, it could be the stock price, it could be some function of the stock price, it could be the indicator function. Okay? We're going to see it with the indicator function. But whatever it is, it just changes the distribution. Just make an adjustment to the mean of Brownian motion. Okay? Add an extra drift and proceed. Do the integration. Okay, any questions? This next part is really where it all comes together. Okay, I'm going to show you the result first. Okay, this is the risk-neutral framework. That's what it tells you. This is what you need to solve. And we're going to solve it as a closed-form integral. Now, you've all priced call options in the exercises, right? You've done it using the PD. You've solved it using the binomial tree, Monte Carlo. Okay. In a sense, the reason we did that was just to get you used to the numerical techniques. Okay. Whenever you can solve the pricing problem in closed form, that's what you do. Okay. That's the gold standard. You solve it in closed form. You've got a pricing formula. It's super fast. It's faster than Monte Carlo or any other numerical scheme. Just do it in closed form. Okay? It's not always possible. It's very rarely possible, which is why we introduced the numerical schemes. Here's a case for the European call option, and that's no little thing. The market in European call options is huge. But in that market, we have a pricing problem. We have a pricing formula, and this is what it looks like. Okay? It's this thing where D1 comes from there, D2 comes from there. Looks horrendous, but you'll see in a moment it's really not that bad. Okay, you ready for it? Shall we go through it? It all fits on one page. Okay? It all fits on one page, and that's supposed to reassure you, because we're going to get here. It's not that complicated. You would be expected to solve and basically do all of this derivation yourself, right? It could be an exam question. Okay. Now, before we start, take your time after we go through it to memorize it, not to memorize it, to understand it, and understand the mathematics behind it. Because at this point, let's put economics to one side. The economics got us as far as the partial differential equation. Mathematics got us as far as the expectation. This next step is all statistics. Okay? And by the way, this is in the lecture notes. Have you been following the lecture notes as part of the slides? They complement the slides very well. I put them together at the same time. So you should have been following the lecture notes as we've gone through the course. Okay. Step one is the definition, risk-neutral valuation, risk-neutral framework. Okay. I'm not going to say anything about that. We're trying to derive the pricing formula for a European call option. You know what a European call option is. Okay. Option at expiry, If the value of the stock is above the strike, you get S minus K, otherwise 0. Okay? This second one, ST, so that's easy. This one is definition. This one you've seen already, okay, week 2. That's just the solution to the stochastic differential equation for a log normal stock. Okay? The key part there, more than the maths, is this. Okay? That's what risk neutral dynamics means. Okay? Right, so this is the expectation we're trying to solve. All I'm going to do is put in the terms. Okay, so ST goes into here. That's all I've done. I'm going to rewrite it, instead of an expectation, as an integral. Okay? And I'm going to work in units of z. Right? That's where this one comes from, here. Okay? All I've done is rewritten it. Now what is this guy in the bracket plus? It means it's either 0 or non-zero. Okay? If it's 0, it makes no contribution to the integral. So what I'm going to do is figure out the domain over which it's non-zero. Okay? How do I do that? Well, the domain over which it's non-zero is precisely the domain over which the derivative pays off. Okay? Which means ST greater than K. We know what ST is. It's got to be greater than K. We rewrite it. We get that. Okay? That's what I'm calling K star. And the benefit of doing it that way is now I can rewrite this integral as this, but get rid of the plus. Okay? What else can I do? Well, because there's now no plus, I can split them into two. I can take this one on its own, and I can take that one on its own. In both cases, I'm integrating from K star up to infinity. Okay? Right, let's look at the first one. Let's look at this one first. That's really not complicated. K e to the minus RT is a constant. You're integrating psi of z, which is just the probability density function of z. So what is that term up there? Expressed as a probability. Probability of z being greater than K star. Okay? This here. What's the great thing about working with the Gaussian? It's symmetric. The probability of being greater than K star is the same as the probability of being less than minus K star. Okay? So you get this term. First term done. Okay? Second term, a little bit more work, but not so bad. Second term is this guy multiplied by the probability density function integrated. And we spent 3 slides talking about why that exponential is special. Okay? All it does, if you combine it with the PDF, is changing the mean. Okay? So this integral now also looks straightforward. It's the integral of another probability density function. So what can you say? What can you say about this? These are just constants. These are just constants. This thing factorizes. This is a Gaussian random variable. This is the probability density function of a Gaussian random variable, variance 1, but mean sigma root t. Okay? So this is just the probability of some variable, some normal variable being greater than k star. Not a standard normal variable, but a shifted random variable. Right? Which is no big deal because you can adjust for that. Okay, you can rewrite it as a standard normal by taking off the mean, by taking off the sigma root t term. Okay? And once again, you multiply by -1, then you get the probability being less than. So these terms here is the cumulative distribution function of a Gaussian, of a standard Gaussian. Yeah? And that's the second term. Okay? As I said, let it sink. Go through it. Once you understand Girsanov's theorem, it's actually very straightforward. Okay? It's just messy calculus, but if you split the terms up nicely, if you write your integrals as simpler integrals, you should be able to follow that. Okay? Any questions on this? And by the way, the D1 and the D2 terms down here, they're just basically K, right? They're basically the K star. So go through it carefully in your own time. There's no homework exercise this week, but what I recommend is that you follow this logic very carefully and then try yourself to derive the pricing formula for a European put option. Okay? Very similar. But you know, things get mirrored around. But if you can do that, then you've understood what's going on here. Okay? Try to do it yourself from first principles. Okay? Try to refrain from asking ChatGPT or looking in a textbook. Test yourself. If you can do that, you've understood the whole risk-neutral expectation pricing formula. Okay? Any questions? No? Okay. All right, look, this is a big moment. Okay, you've just derived one of the most important pricing formulas in quantitative finance. Right? And it fits on one page. It fits on one page if you do it right. If you split out the terms, if you follow the optimize how you think of each contribution to the expectation. Okay? If you use Girsanov's theorem. Now we came up with this pricing formula, and it's just mathematically it looks like an eyesore. It's messy, but it's got to make sense, right? It has to make sense. And with derivatives, we know that there are some natural limits to the price of derivatives. They're not arbitrary, right? Arbitrage-free pricing, arbitrage-free rules stipulate that the value of certain derivatives can't be in this range. Some derivatives, a call option can never be negative, right? Call option price can never be negative. Can you convince yourself that that's the case here? Okay, maybe that's an exercise. Another thing you could do is take limits. What if S goes to infinity? Well, let's do the maths first and then figure out whether it makes sense economically. Okay, so what happens as S goes to infinity? Well, let's look at this term first. S goes to infinity. Well, nothing happens to these terms. Log of S over K. As S goes to infinity, the log also goes to infinity, right? It slows down, but it goes to infinity. So D1 will go to infinity. What can we say about the cumulative distribution function of D1 in that case? Right, goes to 1. What about this term? As s goes to infinity, well, it's no different, really. This term is a different constant. It's not going to play any part. And really, you know it from this result, that if d1 goes to infinity, d2 goes to infinity. So that second term, psi of d2, also goes to infinity. So this thing is going to look something like right? And where have you seen this before? Something very similar. I had two. So somebody said something about forwards, which is not quite right. The boundary conditions of the PDE, right? Remember when we solved, or you solved, the partial differential equation, you needed to come up with boundary conditions which were far away. And we said that as s goes to infinity, the value of the call option, I think you might have used s minus k, which was a less tight boundary condition. But here you can see that the right one to use would be s minus k e to the minus rt. Okay? So at least it makes sense in that perspective, in that sense. What about if this term goes to 0? This term is really the variance of the distribution of S. So sigma and S always come together in this form, right? Sigma and S, sigma and T. T is the expiry of the option, sigma is the volatility. It turns out that they always come together. You always see them as this combination. So what happens as that goes to infinity? What can we say about that? So what's this? You're going to get this term at the bottom, that term at the top. Basically, the numerator is a sigma squared type term, the denominator is a sigma type term. So the whole thing is basically a sigma type term. So d1 is going to go to infinity. Okay? Which means that this goes to 1, right? What about this term? Yeah, now you've got a minus sign. So it doesn't go to infinity, it goes to minus infinity, which means that this term goes to 0. So all you're left with is C goes to S. Does that make sense? As volatility goes to infinity, that means the distribution is very wide. You can have huge payoffs. Huge payoffs means what's the upper bound on the value of the call option? And back in lecture 1, I think one of the boundaries we came up with for a call option was to say it could never be more than the value of the underlying asset. Okay, why was that? Well, let's think about it. Say an option in the market is pricing at greater than the value of the stock. Stock price is $100 today. Call option with strike 120, for example, is trading at $200. Okay, if somebody was, if you could trade that option, what would you do? Okay, sell the option, collect, what do we say, $200. Now you've sold the option, which means that one day somebody might come to you asking you to buy the stock, right? Because you've committed yourself to selling the stock for strike of 120. Okay, so you sell the option, collect 200, buy the stock, keep it ready. And you lock in that $100 profit, because the stock only costs $100 today. Okay? Worst case condition is you keep your $100 profit, but then you sell the stock for some amount of money. You get some, you recoup some of that back. You not only make 100 on day one, but you also make some by selling the option when it's the stock when the option is exercised. Okay. Worst case scenario is it expires worthless. You've got your 100 profit. So there's economics, right? And the formulas kind of make sense in terms of the economics, which is not surprising because all of this fancy maths, you just need to go back to the basics, which is this whole PDE was created to prevent arbitrage. Okay, so it's all encoded in the model. So any price has to be an arbitrage-free price. Okay, just a couple of more points on the Black-Scholes formula. So as I said, try to derive it for the European put option. Right? The answer is online. How you get to the answer is more important. Okay? But there's this concept of intrinsic versus time value, which I'll get onto on the next slide. But very often what you'll hear is people say options are non-linear. What does that mean? Options are non-linear. A forward contract is a derivative which is linear. Okay? With a forward contract, remember, you've locked in a certain price to buy the underlying commodity. You have to buy it. It's not an option. You know, Brent crude is trading at whatever, 62 today. You have a forward contract to buy it at 70 in a year. In a year, if it's trading above 70, that's good for you. You get to buy it for 70 even though it's trading above 70. If it's trading below 70, bad luck. You've got to buy it for 70 anyway. So the payoff is positive, negative. It's very linear. Options aren't quite like that. Right? The options, the payoff is either great if it expires in the money, but your downside is limited. Okay, so the payoff is not linear. Which kind of brings me to my next point. This line, which is the payoff, is called the intrinsic value. The difference between the intrinsic value and the orange line. By the way, the orange line is nothing more than this formula plotted as a function of S. S or K? Of S, okay? So the difference is called time value. So the value of an option is always the intrinsic value, which is easy, it's just the payoff, plus the time value. And it's the time value that Black-Scholes really gives you. Okay? Now what happens as time passes and the option expires? What happens is that the orange line morphs into the dotted line. Okay? The dotted line is what your payoff is at expiry. No question about that. The orange line is the value. So in other words, the dotted line is the value at expiry. The orange line is the value at some date before expiry. But as you approach expiry, the orange line morphs into the dotted line. Now let me ask you, if I said to you, this was the payoff of an option, this was the price, this is the payoff, but this is the price of an option with a half year left to expiry. Plot on the same chart what you expect the orange line to look like if instead I was talking about a similar option, same underlying stock, same volatility, but with a year to expiry. 1 year to expiry. Everyone's doing this, which means it could be up or down. From my perspective, up, right? A little bit higher. Maybe something like that. Sorry, you get the idea. There's more time value. Okay? And why is the value of an option greater than the intrinsic value? If the stock is at price 100 today, and your strike is at 80, you can say the intrinsic value is 20. The option price will be more than 20. Why is that? Yeah, well, you can say that, well, the stock, it's at 100 today with a strike of 80. It might go to 140, but it could go down too, right? So why isn't that a problem? You got upside and downside. That's right. Yeah. That is what nonlinear means. It means you've got all the upside, but not really much of the downside. If things go to the moon, you keep all the profits. If they go to zero, if it goes to zero, you just lose the value of the option. Okay? That's why this intrinsic, this time value is always positive. Not always, for the call option. Next week we'll see cases where they're negative. Right, any questions on that? That is Black-Scholes, and before I release you, I want to cover one more thing. Okay, and actually this is by and large should be revision. We'll talk about the unique aspects next week, but it's the multi-dimensional Black-Scholes model. Okay, so everything we've done so far has been options, derivatives on one asset. Okay, one S. But what you see in the market is actually, you get these funky types of derivatives, basket options, options on multiple stocks, on the performance of multiple stocks. So you buy an option on Amazon, because you're super bullish on tech. You think Amazon's going up. It's trading at 200 today. You buy an option with strike 250, because you think it's going to go up. The option costs you $2. But you're convinced it's going up. So you think this is a great idea. A few months down the line, there's a scandal at Amazon. Hypothetical, just for the video. Disclaimer, there's a scandal, accounting scandal, happens all the time. Amazon goes down. But tech, AI, all that stuff, soaring. Okay? Google's gone up. Nvidia's gone up. Microsoft's gone up. Meta's gone up. They've all gone up. Amazon just, you happen to pick the bad stock. Instead, what if you had bought an option on a basket of tech stocks? Okay? So now instead of just Amazon, your payoff is not just price of Amazon minus K, it's price of Amazon plus Google plus Nvidia plus Microsoft, all averaged somehow, minus K. Okay? That's a basket option. But already you see a complication, right? We can't really use what we've come up with so far. Number one, we've got multiple assets. We've got I equals from 1 to D dimension. This is the multi-dimensional case, right? Each I is a different asset, but each asset can be correlated with the other assets. Okay? That's the correlation matrix, right? You can put them all into a matrix. So normally you have a correlation matrix. But aside from that, each asset is still log normal. We're still going to use the same strategy of replication and self-financing. And just to remind you, the idea of replication is you now take the value of the derivative. The value of the derivative now is more complicated. It's still a function of time, but it's now a function of all of these underlying stocks or assets. That's V. This is your replicating portfolio, which is now, previously you just had delta S, but now you've got to keep a position delta in each of the underlying stocks. Okay? Makes sense? Just an extension. There's still only one money market account, which you use to fund all of your transactions. You can rewrite this like that, because the idea is that you want to ensure that pi, which is the value of this portfolio, starts off at 0, okay, and stays 0. If you know that this guy is 0 all the time, at all times, you know that the value of your derivative is offset by this portfolio. Okay, this is just a portfolio of stocks and some cash in the bank. But this has managed to offset that or replicate that. Okay, that's what we're doing. We're going to assume the self-financing strategy, which means some rule, like Black-Scholes, will tell you how much of each stock to maintain, delta, right? Delta I. How much of each stock to maintain at each time, which means you need to rebalance because delta is not constant. It's going to change from one time step to the next. And this equation at the top is telling you that whatever you need, whatever cash you need to rebalance your stock holdings, Okay, if all the deltas go up, it means you need to buy a few more stocks. Where do you get the cash from? Well, you borrow it from the bank. Okay, D of delta tells you how much stock you need to buy. D of psi just tells you how much more cash to get from the bank. Okay, so it's a closed system. That's the whole point of the Black-Scholes replicating strategy. It's a closed system. Okay, no cash goes in or out. It all comes from the bank account and gets invested in the stock. And if you sell some stock and you have cash, well, you just put it in the bank. Right? You don't put it in your pocket. It goes straight in the bank. Ito's lemma, that's the other piece. So now V is the value of some complicated derivative on the basket of stocks. But you can rederive the Taylor expansion, which is just the multi-dimensional case, right? The only difference now is that you have summation for the first order derivatives from I equals 1 to D, and this is a two-way summation, right? Summation over I and J times dsi dsj. Previously we had ds squared, and we said, well, ds squared, there's a quadratic term in there. It becomes sigma squared s squared dt. All the changes now is that because si and sj are correlated, it becomes sigma I, sigma j, rho I of j times dt. Okay? Same arguments. You basically delta hedging. Remember, we said we want, the whole idea is we want pi to be 0, d pi equals 0. We have no chance of doing that if the portfolio has randomness, right? Delta hedging strips out that randomness. If you strip out that randomness, you have a chance of ensuring that this stays at 0. You can control it. You can't control something that's random, right? By definition, it's going to evolve beyond your control. So delta hedge, but now you've got a position in each stock, but it's still just a natural extension of what you had before. Okay? And then you get the final PD, which is this complicated looking expression, but really it's just the multi-dimensional equivalent of the Black-Scholes PDE. Okay? So this kind of reasoning you should be able to do. Once you've done it a few times, seen it for a few different flavors, have a go at doing it, by the way, for the option on a dividend-paying stock. I think it's in the notes. But have a go at doing it yourself. 1D, but what if the underlying asset is dividend-paying with a continuous dividend continuous dividend yield? Okay? Now the question is, how do we solve this? You've got a PD. If you thought the Black-Scholes PD was long and kind of complicated looking, well, this is just rows and rows of partial differential expressions, right? Now you could solve it using a PD for grid, but you're asking for trouble. Okay, you've all done the exercise. One dimension, one spatial dimension was already complicated enough. If you have two spatial dimensions, you've not got a grid, you've got a cube. If you've got d dimensions, you've got a hypercube. Right? And you've got to remember, you've got to fill in every point in this grid. It's not scalable. Okay, so you can't use the PDE grid. Generally works for up to, say, two dimensions, two spatial dimensions, which in our world means two underlying assets. Any more than that, you're asking for trouble. Okay, what if you try to convert it to an expectation? Okay, and once again, this theorem can get us there. Whereas now we need to assume the risk-neutral dynamics for each asset. Okay, again, it's just a natural extension. This stays the same. You've still got correlations. You apply it to this function. Okay. take some function f, write down the Taylor expansion, keep the second order terms, take the expectation, all the Ito terms disappear. What you're left with, if you rewrite it that way, is the derivative with respect to time, the derivative with respect to each of the spatial dimensions, and the cross derivatives, right, which is the quadratic terms. And you'll find that this is exactly the Black-Scholes multidimensional partial differential equation, which means that this all goes to 0. And that's what you're left with. And that's a great result. Okay, that's how powerful the risk-neutral framework is. It says all you need to do is change the stochastic dynamics of the process, calculate the expected payoff. It always works. Okay? Just that now S is not a scalar, it's a vector, right? This is a scalar function, a multi-dimensional scalar function. But you can still work out the expectation. Now, how do you work out the expectation? What would we do in this case? We've already said PDE, we're not doing it. That's why we came down this route. You could work out the expectation numerically. So you remember from high school, if we wanted to work out the integral of f of x dx, we use like trapezium rule. Okay, area under the curve. Cast your mind back to lecture 5, and you would have covered why this works well in 1 dimensions, less well in 2 dimensions. It really starts to degrade 3 and higher dimensions. Okay, if you do numerical integration on a grid. Theoretically it works, but you're going to need a very, very fine grid, and it becomes unscalable. Okay, where does that leave us? If you can't do an integration numerically on a grid because the convergence is very, very slow, what do we say about Monte Carlo? The convergence is always, regardless of the dimensionality, 1 over root n. Okay? So, what you're saying is you still got this expectation you need to compute. Do it using Monte Carlo. You just now need to generate correlated random variables. Okay? We'll talk about that. Well, you would have covered it already, but we'll talk about it in a little bit more detail next week. But here's kind of the summary. Because you've basically, look, for the rest of the course, there's no more new numerical techniques coming up. You've seen it all. The rest of the course is all about applications. All these numerical, mathematical tools that we've given you, you're going to see them being used. But it means you need to know when to use them. Okay, you've got Monte Carlo, you've got binomial, PDEs, expectations, whether you do it in closed form, whether you do it on a grid. Okay, they're all viable pricing engines, but you need to know when to use each one. So European derivatives, this is a summary, right? If you have a European derivative, non-path dependent, kind of like today's Black-Scholes call option. Whenever you can, do it closed form. Okay, it's worth spending time to figure out whether a closed form solution exists. If the dimensionality is 1 or 2, it's likely that you might be able to find a closed form. If the payoff is just a little bit too complicated, maybe you resort to a partial differential equation on a grid, or numerical integration, right? Trapezium rule, what have you. If the dimensionality is greater than 3, you really need to start thinking about Monte Carlo. Okay? Now, what if you have a path-dependent payoff? What is a path-dependent payoff? So European option says, what's my stock price at expiry? And where's K? Okay. What if I give you this derivative? Or a client calls up saying, I don't want to bet everything on the price on one given day. I want my derivative to pay off based on the average price over the life of of the option. Now all of a sudden, if this is time, and this is S at t, and that's where you end up, with a European call, non-path dependent, that's all you care about. With the example I've just introduced to you, whether the stock does this or the stock does that, very different, because you're taking the average stock price over the life of the trade. So you need to keep track of the path that the stock price took. This is called an Asian option, okay, an averaging option. Now how do you price this? Because you can't do it in closed form. Use Monte Carlo, right? You run a path. On each path you could figure out the average for that path, and then you take the expectation over all paths. Some of them will be of this type, some of them will be of this type, some of them will be in the middle. You take the average, and that gives you this. Okay, these are still European, which means that one expiry at the end. What about American options? Non-path dependent. What's the strategy to solve? Well, what is the American option first? An option which gives you the right to exercise at any intermediate date, right? You don't need to wait right till the end. You can exercise at some point before the expiry. So what techniques have you seen to value the American option? Binomial tree? Yeah? Because the binomial tree works backwards, so you can kind of keep track. You see, with an American option, you have a decision to make. On every exercise date, do I hold the option? Do I exercise it? If I exercise it, I get S minus K. If I hold on to it, well, I know what the value of holding on to it is. Okay, so you use a tree. And if it's 1 or 2 dimensions, that's okay. You can build a 1 or 2 dimensional tree. You've seen 1 dimensions. We won't ask you to build a 2-dimensional tree at any point in this course, but it's just an extension. It's the same idea. If you have a large dimension and it's an American option, then you have a problem. Okay, you can't use a tree. You can't really use, well, why can't you use Monte Carlo? American option with Monte Carlo. Let's say you had an American option, expires in a year, call option, expires in a year, or whatever, some funky payoff, expires in a year, but you have the option to exercise it on the 1st of every month. So between now and the expiry, on the 1st of every month, you've got a decision to make. Do you exercise it, or do you hold on for more value? And the question is, can you use an American, can you use Monte Carlo for this? What do you think? Expiry, 1, 2, each of these dates. These are the intermediate exercise dates. So how does Monte Carlo work? You simulate a path, right? You start off here, you simulate a path. You get to the first exercise date. Well, before we do that, how would you price a European call? You simulate your path, get to expiry, figure out the payoff, keep track of it, simulate another path, payoff, keep track of it, do it 100,000 times, take the average. Right? That's the American call option. Okay, but now you've got intermediate exercises. So you simulate your path up until the end of month 1, the first exercise date. Now what do you need to do? You need to make a decision between intrinsic value, which is always easy. You know the price, so you can figure out the intrinsic value, versus the option of not exercising. Well, what's the value of an option that you won't exercise? The value of an option that you haven't exercised is the value of an option with only 11 expiry, 11 options left, 11 exercise dates left. How do you work that out? Well, you stop there, simulate more Monte Carlos, more paths. But on each of these paths, you get to month 2. Now you've got a decision to make. Either you exercise or you hold. If you hold, run more Monte Carlos, right? Hope you see the problem here. You're kind of doing Monte Carlo within Monte Carlo within Monte Carlo, right? It's very expensive. It's not scalable. Okay? And that's just the first path. You've got to do it all again 100,000 times. You see? So you've got Monte Carlo embedded within Monte Carlos. And each time you need to kind of come back up. It's kind of like, how many people have heard of this movie called Inception? It's a pretty old movie, so I don't know. Yeah, I guess some people have. But it's kind of like, for those who haven't seen the movie, the main characters, I think Leonardo DiCaprio, a few other big actors, and they go into a dream state. And then within the dream state, they go into another dream. And they go into another dream. And each time they need to do something, but they all need to come back up, right, at the end. It's like a dream within a dream within a dream. This kind of like that, right? Monte Carlo within a Monte Carlo within a Monte Carlo. But each time you need to come back up to the state that spawned that Monte Carlo. Take the result and add it on, and then come back up another state. So that's why American Monte Carlo, there are techniques out there, but too complicated. Okay? One intermediate exercise, maybe. American Monte Carlo, by definition, means you can exercise anytime. Okay, I think we're going to call it a night. We will pick up next week. I've still got a lot of interesting stuff to say about correlation. I introduced the idea of the correlation matrix, but we're going to talk about it. Maybe the last point I'll make is that this correlation matrix, even though I've kind of brushed over it, it is quite easily the most dangerous thing in finance. Okay, we'll talk about it next week. Okay, that's it. I'll see you next week.